we're recording. Okay, thank you, sir. Okay.
What was the class average for the exam?
Oh, I don't know.
What about the other class?
The other class was 71, 72.
It's a big improvement from the last time.
Yeah, so, yeah, no. Okay. I don't know. I'm not sure about that. All right. So here's the sequence we know. 2, 4, 6, 8. Come on. 2, 4, 6, 8, 10, 12. I'm going to do something weird.
That's the
2
product
plus
one,
2.
right?
Depends on where you start, right?
Yeah.
And
Go
the
ahead.
geometry one is when
You're
you
trying to come
multiply
up
them
with
by
a formula,
something,
right?
That's right.
true.
All right, so people seem to have some familiarity with sequences, okay? So that's one. I'm going to write another one.
Okay, you got me.
Okay, that's another one. Are they the same?
Plus 4 minus.
No, not the same. So it looks like a list of numbers, and now the order matters. The order matters, so that these two lists are different. Right? Obviously, if you look at the set that contains those numbers, the set is the same. The list is different. So sequence is a list of numbers where the order matters. Now that is, of course, the informal definition. I will ask on the test to define a sequence. Define what it means for something to be a sequence. Here is the definition. What makes this list something special? Well, what makes it special is that there's a first one, there's a second one, there's a third one, a fourth one, there's a fifth one, a sixth one, and so forth, right? That's what makes it special. So it seems like this list is infinite, but it seems like we can count them, right? And we can list them out up to some arbitrary time, okay? So in some sense, because I have this notion of being able to count them in the back of my mind, then it seems like that both of these lists are functions, and they are. Okay, so definition, a sequence, f is a function that assigns each natural number a real number. That's all a sequence is. You put in a natural number, 1, 2, 3, 4, 5. 0 is not natural, although we're going to use it. Right? And then you come out with a real number. Now in this case, I gave you 1, and then 2 is returned. Bringing the natural number 2, the natural number 4 is returned, but 4 is also a real number. 3, 6, 4, 8, and so forth. What does n go to? What does n, if 6 goes to 12, what would n go to?
2n.
2n for sure. I'll take questions about that. All you're doing is multiplying the number by 2.
So that's a geometry one, right?
No, I don't even have a name for this. These are just even numbers. Yeah. Questions about that? So literally, for that example, we would say that f of n is 2n. And here's the notation that we use. We use a sub n is equal to 2n. A sub n is equal to 2n. Oh my God. I haven't even talked about why the hell we're talking about this stuff. I'm sorry. That's just bad teaching. I apologize. That's being bad because that's the way I was taught. So I'm trying to break out of that bad teaching. Chapters 8 and 9, sequences and series. There are some functions, and you'll see this. Engineers, where are my engineers here? 1,
Possibly.
2, 3, possibly.
I would love to.
That's right, absolutely, very good. There's some real, when you start doing some real engineering, you're going to see some really ridiculous functions. Sine, cosine, the exponential, those are just the nicest functions. And again, when the book says an introduction to transcendental functions, we're talking about those nice functions. But there's some weird functions. And the way that we write those functions is in terms of series, right? So Bessel functions and gamma functions. These are the functions that are the basis of physics, engineering. You know, bridges are built based on gamma functions and on Bessel functions. Of course, you ask, what are they, right? I won't be able to write those things until the end of chapter 9, right? But we need series in order to write them. Also, Fourier, some time ago, one of the great mathematicians, he was also some physicist type person, but one of the great mathematicians had to write sines and cosines in an infinite series, right? So we need series to talk about the real functions that we use to model a lot of reality. Okay. Now, in order to talk about series, we need to talk about sequences. Okay. So that is the game plan. So by the end of chapter 9, I should be introducing to you functions that look weirder than the functions we dealt with, but are necessary. Okay, so that we can talk about them later on. That is the game plan. I apologize. All right, so a sub n is 2 times n. All right, so here's another one. 1, 3, 5, 7. Bear with me, bear with me. What's the nth one?
So it's increasing by n plus 2.
N plus 2?
2n
No,
plus
it's
1.
plus 1 something, right? 2n plus 1.
What is it?
So
So this is the first, I'll put it in red. This is the first one, second one, third one, fourth one, fifth one.
So 3.
2n minus
2n minus 1 for sure. So 2n minus 1. So the nth one goes to that. Let's get rid of that. So this is the nth one. So the lesson here, of course, is that put that in black. Even numbers given by multiplying some other number by 2, odd numbers. Ooh. Odd numbers given by multiplying a number by 2 and then subtracting or adding 1. Why am I doing that? N, the letter N. There we go. Okay. Let me give you some extra credit. My discrete people are going to crush this, okay? See, there is a benefit to discrete.
There's a lot.
What did you say?
There's a lot of benefits.
And see, this is precisely what we were talking about, Nick. See, one person, we were talking about this before you all got in there. He was mentioning how he's going to take a class, and someone was telling him that there's no way they're going to take it because Professor X, X is a bad letter, Professor
Whatever.
Z, right, is teaching it, right? And then he said, well, would you ever not take a class because someone else was teaching it? And I said, of course, that makes a lot of sense. And we see it very interestingly. You are just mad, you're married to discrete. Forget about being, madly in love with it.
I wish I had taken it before I had taken intro and
Precisely,
intermediate
but that is completely, other people are taking discrete from other people, and it is completely the opposite experience, right? And we falsely believe that classes are professor independent. And they are not. They are absolutely not.
The
So-
textbook sucks.
Okay, but see, not
It's
that.
the worst textbook ever.
Well,
What?
Do you have to get it?
Yeah. Good.
Yeah,
It's
it's
ridiculously expensive.
Yeah, that's right.
And it just, he's only picking and choosing parts of it because the prerequisite for the class is college algebra.
all right. Here's the extra credit. So, even and odd numbers. Okay. So the product of even numbers, an even number, and an even number is what? Even, absolutely. The product of an odd number and an even number is even. Product of an even, I'm sorry, odd and odd, right? Product of an odd and an odd is odd. That's what I want you to show. I'm gonna do it for addition, just to give you an idea of what I'm looking for. Okay. here's the claim. The sum of two odd numbers is what?
Even.
Even. Right. I also do an even and odd. Okay. Here's the proof. So we'll let x and y, let x be odd, and let y be odd. We need to show that x plus y is even. Right? Well, if x is odd, what remark do we make? That's exactly right. Since x is odd, there exists an n such that x is equal to, go ahead, 2n minus 1. I prefer plus 1. It doesn't matter. Okay? I'm just a positive guy like that, I suppose. Right? And since y is odd, there's a what? There's a what? But what letter are we using? Oh, but what letter are you going to use here? What? M. Okay. X is equal to, I'm sorry, y in this case, right? Okay. Y is equal to 2m plus 1. Why did I do that? Because now, after I decompose it like this, it should become obvious can we argue that this is even? Right, so this is equal to 2 times n plus m plus 1, and that is obviously even. It is the product of some integer, some natural number, n plus m plus 1 times 2, that makes it even for sure. Okay. So when you multiply, you're obviously going to do the same thing. So again, I hope I'm giving away points here. But this is typically, how you prove things. I think in discrete. I wouldn't be surprised if this wasn't given in discrete. Okay. Questions about this proof? That's the end of it. So this by definition is even, for sure. And that's the end. So when you're multiplying even and odd, just go ahead and do it, and it should just, whatever you get at the end when you multiply, for sure should be whatever the claim was. Questions about this proof at all? Even or odd?
That's the question.
We'll make them worth 2 each. I think it's pretty easy. I think they're pretty easy. 2 points apiece. All right, let's write some more. Any question about the extra credit, what I'm asking? Right. I'm just secretly trying to make math majors out of all of you. That's what I'm doing. All right.
Right, that was 2n plus n.
Right, so,
Plus 1.
yeah, plus 1, that's right. And so then that makes everything a multiple of 2 and the game is over. And when you do the odd one, you'll see it pretty quickly out. All right. Here's another sequence. 1, minus 1, 1, minus 1, 1, minus 1.
Diverging.
Whatever that means. Given definitions before I even define things. How do I write this? A sub n equals, these are just powers of minus 1, right? Minus 1 to the, I'm worried about that one.
Plus 1.
Yeah. Okay. Let's put it in different colors.
Well, where does n start?
We have n starting at 1 right now. We're going to start it at 0 soon, I think. But we have it starting at 1. Now remember, look at my definition. My definition says it takes the natural numbers to the real numbers. 0 is not natural. Cultures were afraid of 0. Entire cultures were just spooked by 0. What culture is that? Was that the Mayans? I think the Mayans were afraid of the number 0. No, because of the emptiness and all of that, right?
-1 to the first power would cause a
Right.
problem?
Yeah, because negative. So if I left out, thank you for your question. If I left out this, right, and then I looked at literally ace of 1, I'll keep it in green. If I put ace of 1, that is -1 to the first, and that is -1, and that's not that. So I need a +1 here. I could have put a -1 if you wanted to. That makes it 2, and that makes it a plus. And then we're in the right place. So ace of 3 is -1. Wherever there's an n, you put 2. Right? And that's -1 to the third, and that is -1. Ace of 3 is equal to -1 to the fourth, and that is +1. And it looks right. Oh, there those damn dots again. The constructivist comes in, right, along with the great skeptic. The great skeptic comes in with the constructivist and says that, and the great skeptic says, let me let my friend speak to you. And the constructivist says that, well, you know, you made a bold claim, right? You want me to believe the rest of these things. You want me to believe the rest of these things. But how do I know that this is true for all of them, right? And the great skeptic just smiles in the background, right? And of course we say, you know, you are absolutely correct, right? But we can prove that it remains -1. That formula fits that for every real number, for every natural number, right? How do we prove this, my discrete people? How do I prove a statement about natural numbers? You prove it by, begins with an I.
Induction.
You prove it by induction, okay? So there's a way to do it, okay? So I appeal to outside of the class. There's a way to prove that that is true, not just for the first 3, but for every single natural number, okay? So there will be statements like that that are true for every natural number that I cannot prove in this context. Okay? But I have some people in here who can, right? Okay. So obviously, if I change the signs, right? If I change the signs, then that's not a problem. So let me change the color too. So if I have -1, -1, 1, -1, -1. And the reason I'm bringing this one up is because this one's an important one, because you're going to run into sequences where the signs change, and this is one that this is one of the sequences you need to throw in there to change it. This is b sub n is equal to -1 to the n. Perfect. Okay. That's how you get the signs to change. Questions about that? Remember factorials? Did we define factorials last time? No. We just had the test last time. The exclamation point.
No.
We have not defined that. Okay. So we need to define factorial. The exclamation point. Here's a definition. What's 4 factorial?
4 times 3 times 3 times.
That's right. 4 factorial is 4 times 3 times 2 times 1. 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay. It's hard to write that as a definition. Okay. So here's the definition. I'm going to take this exclamation point, and here it is. 0 factorial is 1. And let me be a little bit more careful here. We define as a sequence, as a recursive sequence. Recursive sequence. As follows. I got some programmers in here, right? programmers? How do you define factorial in the program? Or is it already built in?
I would say it's already built in.
Okay. That's the easy way out. All right. So recursive means that, of course, that the next one depends upon the previous one. Right? That's what recursive means. Or not necessarily the next one, but one step depends upon some other earlier or later step. Okay.
You build loops for it.
Right. Something like that. That's right. So the fact that it's recursive means I need to tell you one. And I am going to tell you one. The first one is that 0 factorial is 1. Now, I defined this last class, I defined this last Thursday for my class. They had their test on Tuesday like yours, and then we had class on Thursday. And I did this on Thursday, and then today on Tuesday, I said that 0 factorial was 1, and then someone asked me, well, wait, why is that again? Why is that?
I mean, you can't get it.
Because I said so. It's by definition. I'm defining what the damn exclamation point is. Okay? That's why. Right? So that you don't need to come up with some. We defined it to be 1. Right? And then how do I get the other ones? If I want to know the next one, if I want to know n plus 1 factorial, it is just n plus 1 times whatever n factorial was. And now that should tell me what all of them are. Okay.
So that's
Questions
not
about
like
that?
factoring out the n,
Kind of, right. So from that, 1 factorial, what is it?
1 times
1 times 0 factorial. And that is 1 times 1, which is 1. Okay? So again, notice how we are as mathematicians. It's got to be solid. You can't just say, oh, let me define factorial. 10 factorial is 10 times 9 times 8 times 7, 20 factorial is 20 times 19 times 18 times, right? You get the idea? That's not going to fly in mathematics. Okay, we got to give it right. Now, of course, we haven't made it clear yet. It's not obvious that this is going to give us what we think factorial should be. So let's do a couple. 2 factorial is 2 times 1 factorial, and that is 2 times, well, 1 factorial is 1, and that is 2. And then 3 factorial, let's get some space here. All right, so 3 factorial is 3 times 2 factorial, and that looks like it's 3 times 2 times 1, and that is 6. And here's a list of numbers you need to know too.
What do you mean?
When I said, because number 2 on the exam is going to be write the first 5 terms of this sequence. I'm giving away points, okay? Write the first 5 terms of some sequence, and then part B is going to be, here's a list of terms, tell me what the sequence is. And if I give you a sequence of numbers that says 1, 2, 6, 24, 120, yeah,
Okay.
we'll do some of those.
All right.
4 factorial, we'll end there. 4 times 3 factorial, but again, that's 4 times 3 times 2 times 1. That is 24. Okay. So again, be on the lookout for 1, 2, 6, 24. Those are factorials, and so forth. Questions about that? So the n factorial, so I choose again n, and here's the way that people think about it: times n minus 1 times n minus 2 times dot 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 3 times 2 times 1. But the actual definition is a recursive sequence. Say it again. What is what? What is which one? This line here? Oh, it's just a generalization. If you want to know n factorial, you'll take n times n minus 1 times n minus 2. So if you have 100 factorial, it's 100 times 99 times 98 times 97. That's 3 times 2 times 1. What'd you say? But that's why it's pretty obvious that it depends, that the next one depends on the previous one. Right? So I'm not proving anything. Right? So I'm just stating what. Oh well, actually, this is a claim, isn't it? You're right. This is a claim, and you would prove this claim by induction. Yes, that's right. Right. So, but obviously obvious that you do this.
Isn't that how you calculate the amount of possibilities or something?
Absolutely, absolutely. Let's do that. So I got some experts here, so I need my experts to be quiet. Right, so now I've got A, B, and C, right? And I got some spots here. I got this one, almost, this one, and this one. And I need to put 3 of them in these 3 spaces. How many ways can I do that? 6. And it's not coincidence that that is 3 factorial. So the number of ways of placing 3 items in 3 different places without, repeating some is that number factorial. And of course we can write them out. ABC, ACB, BAC, BCA, CAB, CBA. That's all of it. Okay? Questions about that? So if I have 4 spaces, it would be 4 factorial. So you can see already that that saves time. That saves time in terms of counting things. How many ways can you do such and such? How many ways can you pick 2 items from 5? My experts?
This is like 20.
20? Whatever 5 choose 2 is, right? It's 5 choose 2. Right. So, no. But so the point is that depends intimately on factorials. That's all factorials. Okay. That's one of the benefits of factorials. Okay, good. Let's do one now. So, question number 2 in the test. I have something like this. Oh, sure. Let's make it 3. We can make this. We can make that all one question. Define a sequence, and then so A, define a sequence. It's a function from the natural numbers to R. It's a function from the natural numbers to R. That's what a sequence is. Questions about that? Because people just, one of the heartbreaking moments over this weekend, grading tests and having to take off 12 points for number 1, just an absolute travesty. I just don't, it's just outrageous. And I know that, some of us crammed for number 1 in the first test, but I'm going to continue to ask it. It's free points. There's no reason you should lose a letter grade because you just don't know what the fundamental thing of calculus is and what the integral is. That is just abominable.
I noticed that from what you use as the practice test that you put up on Blackboard,
yeah,
you asked the same problem 3 years ago.
Yeah, I know. That's why I'm retiring in 10 years if I'm still doing this shit. Yes, it's outrageous. It's ridiculous. It looks exactly, the format's the same. Listen, I can't tell you how many of one problem I've done. There's certain problems that I've done over 100 times over the course of decades. So, of a decade, 1 decade. So, yeah, it's a little crazy. Okay, so define sequences. Okay, and in B, write out the first, again, giving away points. Write out the first 5 terms, right? Write out the first 5 terms of a sub n is equal to minus 1 to the n times, let's say, 2n squared plus 1 over 3 n to the 4th minus 1. Let's do that. So I want a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. Please do that quickly so we can just move on. All right, so wherever there's an n, you put the number, okay? Now, I may make that recursive, I probably will, right? I may say that a sub n plus 1 is equal to 2 times a sub n or something like that. But it doesn't matter.
I don't understand how you do that.
How what?
Negative 1 to the n times?
Yeah, times 2n plus 1, 2n squared plus 1 over 3n to the 4th minus 1. That's the whole
4th
sequence.
minus 1.
Yeah.
Okay. Sorry, it wasn't really clear that was the next exponent.
Oh, I'm sorry. Yeah. A
So
sub
the
1.
first one I got negative 3 over 2.
Why is it a 3? It is a 3. Maybe that's why. So minus 3 over 2. If you plug in 2, you get a positive, and then what is that? 7? 7 over some crazy thing. 242? 247? 81 times 3 is... Is it 9? Wait, where?
2 times 2 squared. I got 9
Oh,
over
yeah, thank you.
47.
It's 9. I apologize. 9. What did you get for the denominator?
47.
47. That's right. I'm putting in 3, not... Wow. So 47. Okay. And then 3?
Negative 19 over 242.
Negative 19.
Over, yeah, 242. Yeah, indirect.
242. And then we'll just leave it. Right, so 4, what is this? With 4? 33? Over 3 times 4 to the 4th.
767.
Feel free to write that if you like. 51 over...
4 to the 4th is 256.
It is. 5 to the 4th minus 1.
So
And I need to change the sign, right? That's negative 1.
3,000. Yeah.
So if you were asked to go back from this to that formula, how would you?
Oh, no, I wouldn't do that. I wouldn't do that. They're going to be something that you should just be able to know.
Would
So,
that be possible to do though?
of course. Oh, yeah. You would be able to see. You just have to, really think hard. Right. So, yeah.
How would you be allowed to use calculators?
Where would you need one? For what? Where would you need a calculator? If I'm taking this as an answer?
I guess if you're letting us use the exponent.
Yeah. Okay, and then C, something like this. What is this sequence? Let's be good. So, what about this? What about 2 over, yeah, 2 over 9 minus 4 over 16. I'll leave it like that. 8 over 25 minus 16 over 36.
How about we have to break it up? We have to use the numerator, find the numerator, and then find the denominator.
Seems like it. Seems like it. Find out what you think this is. What is the nth one? What is the nth one?
Remember we just
Here
said
is
something
the.
about changes.
This is the first one. That's the second. That's the third. 4. N plus 2 squared. I think that's right. So someone already has the denominator.
And you said something about changing the signs.
I did.
So
The first one is positive. I'm starting at 1. What does that mean? Minus 1 to what power?
n plus minus 1? Wait.
Thank you. See, someone's got to say it with some conviction. He's like, plus 1? And then what's the only thing left here? These are 2 to the, absolutely right. Very good. Those are powers of 2. Okay. Yeah, exactly. 3 points, right? That's what I'm saying. All right, so find the pattern. All right. So questions about what I'm asking for this question: define a sequence, write out some terms, and then recognize a pattern.
It's n plus 2 squared, right?
Oh, it is. Thank you. N plus 2. All right. It's gonna be one of those correction days for me. Okay. Questions about this. So what do we have to recognize? We have to recognize that this was 3 squared, 4 squared, 5 squared. Well, 3, 4, 5. That's just 1 plus 2 squared. I'm sorry, yes, 2 plus 2 squared, 3 plus 2 squared, 4 plus 2 squared. Recognizing the pattern.
Will you get much more complicated?
It's a great question. Only for extra credit. And here it is.
Right on time, huh?
Just go like that.
Let's be sick here. So 1, 0, 1, 0, 1, 0, 1. The worst I can get is if I throw factorials in there now, and I'm apt to do that, right? Because, you know, I want you to recognize when you see factorials. Only because you're going to be doing problems later on, and you're going to want to find formulas for things, and you will see 1, 2, 4, 1, 2, 6, 24, 120. You'll see those numbers, okay? 720. All right, so extra credit. What is this sequence here?
Minus n, it can only if n.
And otherwise it's 0. You have to say the other part, right? So you can be blatant, right? But I want it to look nice, right? So, you know, and again, what he said was right, because you can define a function to be whatever you want. If you're defining a sequence, it's a function. You can name your function whatever you want it to name it. But I want a pretty answer, okay? So the extra credit is write this in closed form. Now, here's the hint. The hint is we know 1 minus 1, 1 minus 1, 1 minus 1, and so forth, right? We know that one. Now, I can just add 1 to all of these things, right? If I add 1 to all of them, I get 2, 0, 2, 0, 2, 0, 2, 0. I've already given it away. Okay, so there's some things you can do to this sequence to get that one. Okay. Even an odd. Odd. Oh. See, odd's such a bad number because I want to give it a 1.
Okay, yeah.
But then, because you said odd, now I have to give it 3. That's terrible. That's terrible. 3 points. So just play around with this one, and that one should come out. Let me get some more extra credit while I'm at it. You get an A in the class if you get this one.
Go ahead.
I'll give you an A in the class if you get this one. Okay. It's on the record. That's right. That's right. So yeah, that's exactly right. Here's my sequence. Is A sub n? Now you said nah. You getting ready? I love it. So you start with any number, right? So A sub 0, you pick the integer. You pick the starting number. And we want it to be a natural number. Pick a starting natural number. Every natural number is either even or odd. If it's even, divide by 2. If it's odd, multiply by 3 and add 1. That's what I want you to do. I haven't asked a question yet. Let's play around with this for the moment. Give me a natural number. 13. 13 odd, I'm going to do what?
30.
Multiply by 3, add 1. 3 and plus 1 gives me 40. Even? 20. Even? 10. Even? 5. Odd? 16. 8.
Wait, how long are we doing this?
Oh, forever. It's a sequence, right? So 2, and then 1, and then 4, and then 2, and then 1. Okay. I'll take any questions about this so far.
Just put a formula?
No, that's not my question.
Yeah, what is the question?
I haven't given it yet. I'll give you the question in just a second. Let's do another one. But you can see when you get to 1, it just starts to repeat, right?
Yeah. Or 4 or 2.
Oh, 4 or 2, that's right. Or any even
Any
40,
power of 2.
any power of 2. You run to the end. Okay. Give me another one. 19. I hope, my man, this does not take us 3 hours to do. 7 is like ridiculous. Do 7. Someone said 7 in the last class. I was like, holy shit. We just went. And they were just like, why are we doing this again? 19. Thank you. 58.
About 60,
29.
Yeah.
Oh, God.
Where's the number? Multiply by 3 and add 1.
88.
Is it 88?
Yeah.
You sure?
Yeah.
88. 44. 22. 11. 34. 17. 52. 26. 13. Uh-oh.
40, 20, 10.
Oh, that's pretty neat.
Uh-oh.
Yeah.
How nice is that, though?
That's a good one.
And then...
And 7 gets there too.
Oh, of course 7 gets there, but...
7, 22, 11, 34, 17.
Yeah. So 13 goes back to 1. So this ends up back in that whole 1 thing. Whew. One of these long days. Does that always happen?
And we discovered something.
Does that always happen no matter where you start?
I mean, it seems
Yeah. Does that always happen? For any place you start, does it always go back to 1? That is the extra credit. Does it always go back to $1 million to whoever proves it? It's $1 million bounty on this one. It's an open problem. It's called a millennium problem, and it's called the I think it's the Collatz conjecture. I think, or it's also called the 3n plus 1 conjecture. So the 3n plus 1 conjecture. And it's been proven to be true for the first like 8 billion natural numbers or something like some absurd thing like this. Because obviously this is programmable, right? Well, we want to know that if it's true for every natural number.
Can you hit 9 billion in this problem?
Oh no, it's just that processing power. It's not even 9 billion. It could be like, some number with 100 digits, right? But we've got computers crunching this, right? So we have it up to some obscene number of numbers. It may be like 1 with 1 billion zeros behind it or something like that. So that is the question, right? So there are a ton of millennium problems, all which give you $1 million if you prove it. So, but certainly you get an A in the class. Yes.
You're putting 13 in for n and getting 40. What are you putting in for n to get 20 in the first example there?
Wait, here?
Yeah.
If it's even, divide by 2, yeah. If it's even, divide by 2.
I get it.
So the
You get your answer, and then you have to go back to the condition.
That's right.
Who came up with this?
It may have been Collatz. I think it's Collatz's conjecture.
Oh, what was the question again?
There's no matter where you start, do you always end up at 1? You always end up at 1.
so
How would you go about proving it?
Nobody knows.
Is there a formula?
Has anybody proven it?
No. That's why the $1 million is still out there to be won. You get $1 million if you solve it, and that's why when I get my 10%, I'll give you an A. I mean, that's.
We're studying for free. We're gonna be
Go ahead. No, listen.
Unbelievable A.
I remember.
Getting an F.
For me, that's right. No. Listen, I'm not. I guess should I say this? This is difficult.
Wait, could
Okay.
we ask one of the professors?
Go ahead, please. Ask whoever you want. Please go ahead. Go ahead. It's an open problem. Yeah. Feel free to Google it. Yeah.
How
So.
do you phrase the if it's even or odd in?
No, you have to define the sequence. Once you define the sequence. Oh no. There's no way. There are ways, but just say it in English. I mean, you can do some brackets and do a piecewise function and stuff like that. Yeah.
I was about to say, what can you do besides piecewise?
Oh no, it's definitely defined piecewise for sure. Yeah. Okay. But listen, you know, when I was, 11 or 12, I was trying to prove Goldbach's conjecture and get my $1 million, So. What'd you say? What, with this one? Oh, this is a billion?
Billion points.
1 times 10 to the, even or odd, I'm sorry. Odd, we'll make it odd. A billion plus 1, okay? Points, okay?
You not take the limit as a sub infinity.
Right, and show that that's 1. Absolutely. Well, it doesn't exist actually, because it goes from 124, 124, 124 forever, right? So
There gotta be somebody that did it. Absolutely.
there's some problems that have not been solved, okay, and that's one of them. And so when I was a kid, I was trying to prove this one, that every even number is actually the sum of primes. Every even number is the sum of primes. 4 is 2 plus 2. Right, 6 is. What's 6? No, just 2. No, 1 is not prime.
2 plus 2 plus 2.
No, only 2. You only need 2.
3 plus 3.
Thank you. We're gonna. I guess I'm glad I didn't give this one. So 8. 5 and 3, right? 5 and 3, and then 60.
Sorry, what's the first?
Prime numbers. Prime
Oh,
numbers.
okay.
For every even number, there are 2 primes that add up to it. Right. So.
Why is 1 not?
Because I think that's in the definition. So it's a number bigger than 1 and it's only divisible by 1 in itself. Right? So 2 fits it, and it's obviously the only even prime number, and then all the other ones only have its divisors 1 in itself, and so forth. So that one is also open as well. So there's $1 million for that one. And again,
So it's only every even number?
every even number is the sum of primes. Every even number is the sum of prime numbers. Sum of 2 prime numbers, exactly. Actually, they've shown it for 3.
So was that extra credit question like a joke?
No, it is not a joke.
Well, what do you, I mean, if it's not, what do you want? You want
I want the proof. I want the proof.
I want to see you put that on the blackboard.
Yeah, that's right. I want the proof.
Yeah, if I get this right, I want to see that in my grade.
That's right. That's right.
I want that on my grade.
That's not a problem. That's right. Forget about the name. You want 1,000,000,001 points,
So you want to.
and the hope to distribute them around.
Schools will be confused as hell when they see that, but I want that on my.
That's right.
GPA
What'd you say?
GPA would come up with.
Exactly. That's exactly right. No. So there it is. So okay. All right. I'll take any questions about what we've discussed so far. I am going to be interested in what happens to these sequences as n tends to infinity. So a sub n equal to, for instance, e to the n over n squared plus 1. B sub n equal to, let's say, let's do this. N squared plus 6n plus 4 all over 3n squared plus 7n plus 12. By the way, Western mathematicians solved one of these problems. Perlman proved, I think it's Kepler's conjecture. And Kepler's conjecture says that the tightest, to create a volume, I can't state it, but he got $1 million and he decided not to take it. He didn't want it.
What do you mean?
He proved the conjecture, Kepler's conjecture, and said, "No, I do not want the money." That's what he said.
Was that the Russian guy?
That was the Russian guy. See? I'm not making it up. That was the Russian guy. Yeah. So this happened like 3 or 4 years ago. That's right. Yeah, but he was a recluse. He just lived in the backwoods of Russia. It's true. C sub n equal to, let's do this one. Let's do 10 to the n over n factorial. My question, of course, is what happens as n goes to infinity? So what happens? So e to the n, the exponential, that goes to infinity. N squared plus 1 goes to infinity. The ratio, indeterminate, that's right. How do we resolve that? There's a rule. L'Hopital's rule.
Oh,
Now, who's never heard of L'Hopital's rule?
You had to take it in calculus.
L'Hopital's rule. I can't even say it wrong. I can't. I tried. L'Hopital's rule, right? Anyone not seen that? Who has seen it?
I have to.
Okay. Have you seen it?
I saw
See, the problem is that some Calc 1 classes do it, other Calc 1 classes don't, right? So here, it's in the syllabus to do it in Calc 2, and I can see it's because of problems like this, okay? And but I've learned it in Calc 1. I've taught it in Calc 1. It's in section 4.4 in Calc 1.
It was very brief.
It's very brief. Okay, and I can understand that because they really situations don't come up in that context in which you have to use it, but they come up in this context a lot. Okay, because now we're going to have this list of numbers, and we want to see what happens as n tends to infinity. Okay. So this goes to infinity, that goes to infinity, so we have the ratio of infinities. And so to handle this one, we want to know the limit as n tends to infinity.
Which one goes faster?
Yeah, that's exactly right. So
E to the n goes faster.
that is what we are about to demonstrate. That's exactly right. Right. So L'Hopital's rule says that if you have the limit as x tends to infinity of f of x over g of x, and if each one is infinite, then we're really not asking about how big they get, but we're actually asking how fast are they moving. Now, I'm not going to ask you to use L'Hopital's rule, but I am going to use it today to get a hierarchy of sequences. What I would like to do before we go on break is to talk about which sequences go the fastest, at least the reasonable ones go the fastest, and which ones go the slowest, so that we can look at a sequence that's a ratio of some of the sequences we're going to talk about, and you can immediately say, oh, that's 0, that's infinity, that converges, that diverges. I'm not giving definitions to those terms yet. Okay. So this one here, this is equal to the limit, and let me go ahead and put 1 in here. I've changed the problem. E to the n over n plus 1. This is equal to the limit as n goes to infinity. Well, both of these become infinite, and so I'm going to use L'Hopital's rule, and when I use it, I'll denote using it by that symbol. That's equal to the limit as n goes to infinity of the derivative of e to the n, and that is e to the n, over the derivative of n plus 1 with respect to n, that is 1.
Is it not n times e to the n?
The derivative of e to the x is e to the x. Right? Right. And this is right infinite. That diverges. So we'll say that something converges or diverges. Something converges if that would be a number. It would divergent otherwise. Someone in my class earlier today said that was trying to equate being infinite with being divergent, that they're exactly the same thing. Can we think of a sequence that does not converge and is therefore divergent, that does not go to infinity or negative infinity? We've already seen a couple. Say it again? Negative 1 to the n, that's right. Negative 1 to the n goes from minus 1 plus 1, minus 1 plus 1, minus 1 plus 1. There is no one number that approaches, right? So that clearly diverges and yet stays bounded, right? Of course, the sign of pi n, right? Something like that always stays between that one's always 0. But the sign of n pi over 2, right, goes from minus 1, 0, 1, 0, minus 1, 0, minus 1, and so forth. Okay, so yeah, that's right. Right. Questions about this? Okay, so that's infinite. The remark I want to make, of course, is that you can put any power here that you like. We showed this in Calc 1, that e to the n crushes any polynomial. Will just absolutely destroy it. And so what does that mean? That means that in this context, if you put the exponential over any polynomial and take the limit as n goes to infinity, you'll get infinity. Right? Informally, we'll say that e to the n dominates polynomials. That is the terminology. E to the n dominates n plus 1. So that means that if you put e to the n over n plus 1 and take the limit, you get infinity. Equivalently, you could say that that means if you take the limit as n goes to infinity of n plus 1 over e to the n, you get 0. Absolutely. So you can say it either way. So e to the n is up there. So the hierarchy is pretty high. E to the n is one of the biggest ones.
Is it above n factorial?
That is precisely why we're going to do this one. That's why I've asked it. Thank you, sir. This is a Calc 1 problem. What's that one? Let's knock it out. B? 1 over 3. That's right. When the powers are the same, you take the ratio of the coefficients. Okay. If the power in the numerator was higher, it's infinite. It's plus or minus infinity, depending on the signs. If the power in the denominator is higher, it's 0, regardless of the signs. Right? So we did that in Calc 1. You would prove that by taking the highest power in the denominator and dividing the numerator and denominator by that power, and then the only thing that would be left would be 1 over 3. Or you would use L'Hopital's rule twice, and you would get 1 over 3. Okay? So there's that 1 over that 3. That's the Calc 1 thing. Okay. Questions about that? Let's answer his question. 10 to the n. And let me do one for 2. It's not really going to matter. Let's do one for 2 to the n. A sub n equals, let's make it 3 to the n. That's bigger than e. And to make the point clear. You'll see why I want to choose a smaller number, only for the proof that I'm about to give. No using L'Hopital's rule here, right? X factorial has not been defined, right? Notice that if I'm going to use L'Hopital's rule, then I need to be taking the derivative of what? Something, Lord have mercy, that's actually dead on right. Something that has a derivative, right? So that means it has to be smooth, right? I have not defined, so when I had e to the x, I know what e to the 2.32789 is, right? I know what e to the 5.63842 is, right? So those are continuous things. But I don't know what 5.6382 factorial is, right? So I can't define the factorial as a continuous function. I certainly couldn't define it as a smooth function, so there's no way that I would be able to take a derivative of it, right? So if I want to show that n factorial dominates 3 to the n, if I want to show that, then I have to do something else. If I want to show that, I need to show that this is 0, but it's going to even be more demonstrative to show that this is infinity. I prefer to show that that's infinite, because the proof is a little easier. Or it just looks better. Right? Proof is exactly the same, but this makes the point pretty clear. Very simply, this is equal to 1 times 2 times 3 times ... n. There are n of those, all divided by 3 times 3 times 3 times a bunch of 3's.
Wait, you just switched that?
Yeah, I switched them. I flipped them. I did.
You can just do that?
Oh, no, so in order to show, yeah, because why can I do that? Thank you, again, keeping me in check. I love it, right? So why can I do that? Well, I want to show that n factorial is going to get bigger than 3 to the n. I can show that in one of two ways. I could either show that 3 to the n over n factorial goes to 0, or I can show that n factorial over 3 to the n goes to infinity. And I prefer to show that n factorial over 3 to the n flies off to infinity, that 3 to the n cannot, even though it gets big, cannot pull it back down to Earth.
So therefore, if you flip it the other way, you can tell what it would be, right?
Yeah, if you flip it, I'll do it both ways. If you flip it the other way, you're going to get 0 for sure. Okay.
I don't understand them multiplying 1 times 2 times 3. 3 is not a factorial.
Because.
Oh, it is a factorial, but it's in factorial.
Yeah.
Remember, one of the comments we made earlier was that in factorial, where is it? Was it there?
I didn't write that.
You didn't write the one for in factorial? Where is it? Is it here? Yeah, in factorial is n times n minus 1 times n minus 2 times all the way down to 3 times 2 times 1. That's in factorial. Again, 100 factorial is 100 times 99 times 98 times 97 all the way down to 3 times 2 times 1. Right? So in factorial is the product of n and all the numbers less than it, all the natural numbers less than it. Okay. Sir?
Why 3 times 3 times 3?
That's the definition of 3 to the n power. 3 to the third is 3 times 3 times 3. 3 to the fifth is 3 times 3 times 3 times 3 times 3. 3 to the nth is 3 times 3 n times.
Okay, so in that case you only pick a number 3 for n, right? And that's simple.
Yeah, that's right. For 3 to the n, this is precisely what it means.
Okay.
Yeah. Can we see why this is going to be infinite? Past this point, what do we know about everything in this numerator? They're all bigger than 3. That's right. Particularly n over 3. Right? And then n is tending to infinity, so the whole thing is infinite. And that's the end of it. Of course, now when I do the opposite, I'm going to make everything less than 1 except for the last term, and then everything's going to 0. Questions about that? It says n tends to infinity, a sub n tends to infinity. Let's do it the other way. B sub n, if we let b sub n be 3 to the n over n factorial, which is actually going to be an important sequence for us, then we have that this is just 3 times 3 times 3 times 3 n times all over 1 times 2 times 3 times 4 times n minus 2 times n minus 1 times n. The n of those terms. And then we'll see eventually after this point, everything here is less than 1. I don't care about the beginning. So here, everything here is less than 1, and this is this number. So this whole thing is less than or equal to, what is this number? 9 over 2? 9 over 2 times 3 over n. Did we see that? Those 3's cancel. That's 9 over 2. And everything is less than 1, so I can replace everything with 1 except for the last term. And of course, that tends to 0. And this is always bigger than or equal to 0. So I have a sequence of numbers that's always bigger than or equal to 0, and it's always less than or equal to something that's going to 0, then that means that the sequence itself has to go to 0 itself. Right? That's the squeeze theorem. Remember that theorem? The squeeze theorem, it's, some people call it the sandwich theorem, other people. So this sequence is squeezed in between two things. Is to say that if someone was standing in front of me, right, and there's the wall, and they always have to be between me and the wall, and I'm a sequence, right, and I'm going to the wall, and they're always between me, then they have to go to the wall too.
We talked about this in Calc 1?
Yeah, the squeeze theorem. You have two functions. Wow. I know. You have two functions. Here's the classic example is you get something like you plot x squared along with negative x squared along with x squared times the sine of 1 over x. We could have made it 2 over x, that's fine. Right. And so usually I would give you x squared the sine of 1 over x and ask, what's the limit as x goes to 0? What's the limit as x goes to 0 if x squared times the sine of 1 over x? And of course, everyone wants to just put the 0 in there and to see what you get, but you can't do that, right? So you have to do something else, right? So one of the ways that we show that this is 0 is that we use this theorem. So x equals negative 1 to 1. And so x squared, of course, is the red graph, minus x squared is the green graph, and the sine graph is in between, right? Now we have no idea what happens at 0, but I'm pretty confident that it's 0 because it's always between the two graphs. Right? So the x squared times the sine of x is always between minus x squared and x squared, and the closer you get to 0, that still remains true. But I know that at 0, x squared is 0, negative x squared is 0, and x squared sine of 1 over x is always in between. So that has to be 0 too. Right? That's the squeeze theorem. Never seen that before in your life. I tried to hit some memories, rekindle. Anyone else seen this example? Oh my goodness. Yes? No? Oh my goodness. Okay.
I thought I was the only one.
Okay.
I kind of missed something with what we were doing before, though.
Okay.
I still don't understand why you flipped it.
Oh, okay, I'll talk about that in a second. Go ahead.
I was just going to ask what happens with 3 to the n over e to the n.
Oh, we'll do that. Oh, yeah, we'll do that in a second, too. Other questions about that? About this? About the squeeze theorem? This new revelation from Calc 1? Yeah. Okay. But that's what we're invoking here. I have a sequence of numbers that's always between 0 and some other sequence that's going to 0. Then the sequence itself has to go to 0. Okay, so I flipped them only because for convenience. I thought it would just be better to demonstrate. It was just a teaching exercise. But the point is that they're equivalent. That if I told you I had a fraction, and the fraction is going to infinity, it's a ratio of two sequences, and it's going to infinity, then the numerator is bigger than the denominator. If I give you another fraction, and the fraction is going to 0, then the denominator is bigger than the numerator. Either statement there is going to tell me something's bigger than something else. So either use the numerator going to infinity or the denominator taking it to 0. Either one is going to tell us that n factorial is bigger than 3 to the n. That's all I'm saying. So I just wanted to present two different arguments to show that that n factorial is bigger than 3 to the n. So they're two separate things. We'll talk about it at the break. And then 3 to the n over e to the n. That's an important one. Oh, is that right? 3 to the n over e to the n. Now we're comparing two functions in the same class. So, yeah, two sequences in the same class. Where does that go? 3 is larger than e.
It's just like 2 something.
That's right. I got a number bigger than 1, and I want powers of it. That thing's going to diverge. That's right. If I have a power, and we'll do that in the next hour or so, I got a power bigger than 1, I'm raising it to the nth power, that thing's going to run off. Even if it's 1.000000001 to the nth power, it's going to go off forever. That's why it'd be nice to live forever. If for any interest, any account will give us a ton of money if we wait long enough, right? So, questions about that. And so obviously, here's the remark. I'll be using this later. I might as well say it. That the absolute, that r to the n, tends to infinity if r is bigger than 1, and r to the n tends to 0 if the absolute value of r is less than. Okay. So, I mean, you take powers of 1/2, that thing goes to 0, obviously. Right? Why? Because you're taking half of something, right? So the first one's 1/2, the second one's 1/4, the third one's 1/8, the next one's 1/16. You just keep taking half. Nothing's going to be left.
So if it was 0.9, then it would...
0.9's got to go to 0 too, right? And so what happens is we do 0.9, we use 0.9 in probability a lot, right? So one of the things that happens is using the AND rule, that if two events are independent, A and B, then the probability of A and B is the probability of A times the probability of B. So that if I ask, what's the probability that if I flip a coin here and get heads and roll die here and get, a 6, then the probability of one and the other is merely 1/2 times 1/6. The probability is 1/12. Okay. But what's interesting is that, you get powers of 0.9 when you say, well, how did something happen, right? And then you say, well, if the probability of A is 0.9, and the probability of B is also 0.9, then the probability of A and B is 0.81. It's 0.9 times 0.9. But if you put a lot of those events together, then it becomes unlikely, right? This is why it's difficult to win a poker tournament, right? Because, you know, you get into a hand and you have, you know, aces versus kings, you know, and just brilliant people like Phil Hellmuth and all these great poker players just get so upset when they get knocked out of a poker tournament. But they get in with aces versus kings, and it's 80% to win, and they win that one. And then later in the tournament, they get aces versus kings again, and they're just playing perfectly. And they're doing exactly what they're supposed to do, and they win again. But that should only happen 80% of the time. But then they get aces versus kings again. I'm giving the perfect scenario, right, for someone why it's difficult to win a poker tournament. Even if you get aces versus kings, in order to win these 5-day World Series of Poker tournaments, you need that to happen. Yeah, 5 days, $10,000, $9 million to the winner. Okay, and so you need that to happen over and over and over again. So even somebody who has someone dominated, you know, 80% over and over and over again, if you got to do that 9, 10 times in a row, then you get 0.9 to the 10th power, and that's not that much, right? So that the probability of winning one of these things is really, really low because.
And the question is, how do you have consistent winners?
Oh, because, well, so what happens, of course, is that that's a different sample space. So versus, think about those people versus the people who get their money in at 40%, right? So even though it's unlikely to win at 90%, those people are still much more likely to win than the idiots who get in with 46% or 52% all the time, right? So those people are going to be winning much more. So the people you see, of course, are the 90%ers, right, versus the 40%ers, but you don't see the 90%ers that often because it's just so difficult, right? And so the great debate is, you know, which one is harder to win? Is it some game that has 50 people who are all the experts, or is it the 10,000 person event with a bunch of novices that you can get in with 90%, or, you know, the 50 people who know the game better than anyone on the planet, and it's like a toss-up against them, right? Less people, but the other one's a minefield, right? So that 90% comes up all the time, right? So it's difficult to really win, or to do even with 90%. If you do it too often, it's going to go to zero. Okay. Questions about this? We'll be using that a lot in the future. All right. Here's the hierarchy, and then we'll break. So I haven't had to prove this, but n to the n is the biggest one. All right. Now, we can get sick. We can have n to the n to the n to the n to the n, right? Well, in the context of this problem, say it again. I didn't mean it. Thank you. I'm going to bring it down here. I appreciate it. So n to the n is the largest, and then n factorial, and then e to the n, and then powers of n. And let me not be biased. 10 to the n, 20 to the n, and then n squared, n to the 7th, n to the 20th, any of those, and then of course the poor natural log increases. That n is so far from the natural log. Doesn't look like it's connected to it. The natural log of n, and I'm being biased, log base 10 of n. That increases the slowest. That goes to infinity the slowest.
So e to the 10 and 10 to the n are pretty much the same speed or equivalent?
Right, yeah, they're multiples, and it's because of the change of the base formula, right? Okay. So yeah, there's some constant, or maybe it's the power of n. But no, 10 to the n crushes e to the n, there's no doubt about that, because 10 is bigger than e, but they're in the same class of family, okay, in terms of increasing, yeah, how they increase.
N to the 1/2 goes to infinity.
N to the 1/2 goes to infinity. The square root of 100, the square root of 1,000,000, the square root of 1,000,000,000,000. It's going slow, but it's going to get there. And again, the great skeptic comes in and says, I don't believe it goes to infinity, and then you just crush him because he says, I think there's a number that the square root of n stays under no matter what n is. And of course, you just pick n to be his number squared plus 1, right? So he says, I don't think it goes above 1,000, and you say, well, 1,000,001, you take the square root of 1,000,001, that is more than 1,000. And he says, okay, wait, I'm sorry, I meant 2 trillion. And you say, well, when n is 2 trillion, I'm sorry, 1 trillion squared plus 1, take the square root, that's bigger than your number. What are you talking about? And he says, okay, you're right. So, questions about this? What do I mean by this? This is the hierarchy. I'm thinking about asking this on the test. Okay. So the hierarchy of sequences. When I ask you the limit of one over the other, anything up here divided by anything below it, it's infinite. If you take anything down here and divide it by anything above it, 0. Okay. These first three here, the bottom three, we proved in Calc 1 using L'Hopital's rule that these dominate this. And it's because the derivative of e to the n, the derivative of e to the x, stays solid. The poor polynomials, you take the derivative of x squared, you get 2x. You take another derivative, it's 2. You take another derivative, it's gone. Right? The derivative decreases the value of the polynomial, yet the derivative of e to the n, just stays rock solid, right? So by L'Hopital's rule, the first three has been solved. We proved that n factorial dominates at least 3 to the n. The same argument shows that n factorial dominates 20 to the n. And then, of course, you can see that n to the n is going to dominate n factorial, I hope. Okay. We'll break there. At 8:05, we'll come back and we'll start talking about series.
I kind of get how you said that the 10 to the n and e to the n are kind of equal because e is just a 2 point something, right?
Yeah, it's just a number. That's exactly right. Yeah, that's right.
I was like, I was waiting 50 minutes for my car to go.
Oh, no worries. People are having car problems. Have you gotten your test?
No.
I'll get it somewhere in here.
Here's some extra credit.
Okay. I am taking extra credit, by the way. Oh, I have a test degree. I don't even know how I missed that.
I was just saying, you can just get back to me, I'll work on a little bit.
These all the tests?
Yeah, they should be there. If not, they're here or here. I need a pen. Do you have a pen? No? What's your last name?
Matt Thompson.
Oh, that's you. No, you're not there, but I saw your name somewhere. Can't do it. Yes. Oh, I need to grade yours as well. Sir, how may I help you?
Extra credit?
Thank you. We need to put extra credit right here. Okay. Yeah. Okay. Good. That's right. And then
Is there extra credit in the final? Or is that too much?
there might be. I'm thinking if there's something that we discuss between the
How close is the last test to the final? We review
a week or so. Yeah, we're going to review like the whole last week for the final. Wait, what is going on with the units here? So, is that right? So, where's this 4 coming from? Is this you, this issue? What is this 4? Oh, this difference here. So, right. So I try to do like the rate of change. I think that's okay. So that's, oh.
So that's going to give us time at 55 minutes, we use time 0.
Right, but why is it not a natural log? So this is 98, at the later time, it's 90.6 is the action from e to the minus 5k. So
I was trying to figure out the way that the code is. No, all since I looked at it.
Man, I don't know how we drew this.
Was it for just run or was it for like something
for his astronomy class.
Wonder what they do in there. Is the teacher graded?
Sir.
He read it.
Well, no, I didn't have a problem with it.
What is the solar system for like that? Well, he actually added the two moons, so she, right?
Is it really linear? But is it linear like that?
I don't know what it's supposed to
The
be.
sun has to go through all of these things, doesn't it? So
It just looks funny.
It
it's
does.
just a unit.
I understand. Oh, so you made time 11 or
The
12.
space
Okay.
is called-
Okay, no, and that's probably, okay, so that's perfect. I didn't think anything off.
Or something.
Yeah, that's.
It's on Google if you look
Okay.
at Google Images.
No, that's fine.
That's what they call it. I
Of
don't
course
know
you
why.
can, or
It's
should I
just
write
like
out that?
But then I think everything else
Happy
has to
smile
change
face.
because everything else is
Looks really
aren't there some,
It's just easier to plug in one.
I agree with that, but aren't there, yeah, I just told a bad story. They should like check the temperature the moment they found them, right? But
But once you
doesn't
get it down,
something change here if you don't assume that time is 1 hour? Is it something subtle?
No, I mean,
guess not.
Because it's a unit. You treat it as a unit.
No, I think you're
Once
right.
you're trying to convert it to find the actual time of day, you just have to make sure.
Oh, no, and then zero still remains zero, so. Zero remains zero. So I guess that's right, yeah. So,
I mean, I just gotta make sure to multiply it by proportion, but I.
yeah, no, I know what you mean. Right, no, but yeah, I've learned something. That's good. That's good. Yeah, that's fantastic work.
Everything else was, right?
Yeah. No, no, 16.
I was sure. I mean,
Yeah. Yeah, I got you. Oh, no. You think I'm going to give you 0? Come on. No way. No way. Yeah.
So I'm impressed with the rest of this is right. I didn't really think I would miss 13 in that one. I guess I didn't think about that long enough.
Yeah. No, it's okay. Yeah.
What the? Oh,
You all right?
because I plugged it in, but the thing is like low battery still. I'm like, I plugged it in.
The amount of effort applied is definitely worthy of an 8.
Okay, good. That is good to hear.
Because I had a physics test directed to see.
I keep hearing that, right? And so physics and I are keep butting heads.
Not last time. Last time was good.
Oh, where were the dates then?
Oh, they were way apart, like weeks.
Are you serious?
Yeah, I've already had 3 tests in there, so test 1 was long before our test 1.
Oh, okay. I gotcha.
But test 3 happened to line up with test 2.
Wow.
And it is much on the first grade.
Well, see, y'all need to let me know that. Just say something, and I'll move it.
Oh, no, it's...
I'll move it in a second. Because he had physics, chemistry, and calc on the same day. No, biology. That's what it was.
Yeah, there's no room for whining here.
No room for whining?
No.
Last week I had cell bio, physics on Monday, and then the conference.
Yes, it's test time, I guess. Oh, I forgot to give you something different. That's right. So what the hell's going on here?
It shouldn't take long if you focus on it, but...
That's correct.
I don't know what to do. This was the test that did you do any homework? It was pretty intense, and you didn't ask me questions, but I know that's
And this is one of the faces. Oh, that one? Yeah, it's kind of somewhere still.
Wait a second, so...
Was it not a practice? Was it not a practice? It's not even practicing that fine. Okay, it's only really what the put together.
I said not even, they had 2 parts, not the second part.
After the second part.
Yeah, it's okay though.
I think.
Don't worry about it. Don't worry about it. It means no, that's what it is.
It's with too many That's how it was. Is the final worth more or the same?
Oh, and the syllabus is the same, but in my mind, it's more.
Wasn't that a 200 last year?
Oh yeah, because there were so many problems. But I still just take the percentage.
Oh.
Yeah, multiply by 22%. So I mean, that just accounts for people having an off day, you know. What'd you say? Or very off days, hey. Then the final becomes redemption. It is. Put the extra credit there, make sure it's there.
No, I just turned mine in a minute ago, but
Oh, okay. Make sure it's right.
I want you to look at it now.
Yeah. Oh, you want me to look at it? Oh, okay.
If I can find it.
Oh, well, is this it?
Yeah.
Okay. So.
I really don't know.
This is good. Now, wait 1 second. So, right. Okay, but wait 1 second. So now. No.
This question was cut off from the PDF.
Okay. Okay.
I may
So.
not have actually solved it.
But this is. Let me see here. So, this is equal to something else, though. This is equal to like t. This is equal to dt, right? And then you have to integrate that. So it's equal to. Yeah. So no, that's not it.
What's
so
this part?
that may be right. That may be right. So I can certainly add that. Yeah. But anyway, we can meet because again, I got a per person policy. You know, if you're not doing well, I got some things you can do. It's just hazing, right? But you know, I got some problems you need to answer. That's right. I got some problems you can answer. That if you can answer, then I'll give you some points. That's all. Wait, I shouldn't say hazing on word. Yeah, that's not good. So. Yeah.
How come most professors can't be like you? This is a great opportunity. Extra credit.
All right. So what you have to do here is you have to divide both sides by this. So bring this over here. So y prime. No, you're dividing. So it's y prime over. You divide the whole thing. Y prime divided by 4y minus 16. So yeah, that's right. Yeah, that's right. Y prime.
That's what I want. I just want to be.
16 equals 1. So you divide it by 4y minus 16 both sides. And now you integrate both sides. Right. That's right. That's right. And I think you're using the letter T, so it's dt.
Okay, so here, I don't need to go to this part.
You didn't go to the whole thing, so it's 1 over 10. It's the number of all.
Why is that? Why,
Just dt. But I mean, it's 1 over that. It's 1 over 4y minus 16. No, it's 1 over 4y minus 16.
Okay, if you do that in the homework, you have to do every single one to that
And then that becomes a natural law.
Okay. That's what I thought.
Right, exactly.
So pretty much problem. So if I fail everything, okay, are you really trying to get an A or are you?
Yeah, so it's t plus a constant. Yeah. And then you just need to integrate that. And you just solve it. Yeah.
Just, I would try to.
So that's like 1/4 of the natural law.
Because I forget your A. You know, my friend said in the as soon as you go in there with the professor,
Yeah, because you get back to
out here, the more you'll be.
That's what you're talking about.
That's what I'm saying, football game was.
Much more.
We can still do it, because I usually go.
Yeah, exactly. And that becomes a natural law.
I would love to.
I studied on the first one, I really did.
All right. I'll take any questions about anything we've talked about. Anything? Please.
Restate hierarchy and the something over something is always going to do something.
Right, thank you. So, I think I know what you mean. So, I have a list of sequences, and here I've delineated them at least by family, whatever that means, right? So, this is one level. We'll use this. This is one level. This is another one. This is another one. This is another one, and so forth. The size of these sequences go in this order. Okay, so the mathematical way of saying that is by taking ratios, right? So the way we show that one thing is bigger than another, if I am 5 times bigger than you, then obviously that means that if I'm divided by you, then 5 comes out, right? If something is 10 times bigger, if A is 10 times bigger than B, then A divided by B is 10, right? So in order to measure how something is bigger than something else, you take the ratio and a big number comes out. Now, an equivalent way of saying that is that if I am 10 times bigger than you, then you divided by me is 1 over 10, right? You are a tenth of my size, right? So A is bigger than B by a factor of alpha if A over B is alpha or B over A is 1 over alpha, okay? So the way that we measure how one thing is bigger than another thing is by dividing. In this context, I know that n to the n over n squared, as n tends to infinity, is infinite, right? Because this is much bigger than this. Right? So if I take any of these above and divide it by anything below it, and take the limit as n goes to infinity, it's going to be infinite.
So would this be right? This is what I wrote.
I may steal it if it's well enough.
I wrote down, if you go down like this over this, it would be infinity. But this
Yeah, I like it. I like it. It's not good enough to steal, but I like it. If you remember it, it's good.
That sounds
Yeah. Questions about, yes. Is that okay? No? Yes? No? Okay. So, okay, good. Thank you. I appreciate it. Just let me know. So for example, the limit as n tends to infinity of n to the n over e to the n, infinite. The limit as n tends to infinity of log base 10 of n over n to the 4th, 0. And it is simply because of the line it's on. So n to the n is all the way at the top. Nothing beats that. And so n to the n over e to the n is going to be infinity. Log base 10 of n in a similar way is below everything. So n to the 4th is right here. It's in this category. If I divide it by n to the 4th, I get 0. Right? So if you take any of these and you put something above it, like in this case, e to the n, you put something above e to the n, e to the n level, and you take the limit as n tends to infinity, you get infinity. But if you take log base n and take anything above that, but then you divide, you're going to get 0. And it's because of the nature of fractions when n is big.
So you argue that all go to infinity in decreasing order from the top?
I like it.
That's what
They all go to infinity slower and slower from top to bottom. That's right. Other comments? Anyone else want to explain it?
Those are the standings in a competition.
These are the standings. I know. These are the standings in the competition, and this one's the best one, and the competition is ratios. Any other ways of thinking about it? Okay. So I'll try and come up with better ways to say it. Series.
So sequences is chapter 8, or are they both sequences?
I think chapter 8 sequences in series. Yeah, yeah. So now, what I want to do is I want to have a list. 1, 1/3, 1/9, 1/27, 1/81, 1/243. These are all powers of 1/3. I'm going to use K as the number. A sub K is 1/3 to the K, and now K is going to go from 0, 1, 2, 3, and so forth. So I'm going to start at 0. Typical sequence. What does it go to as K goes to infinity? It goes to 0 for sure. Right? You keep taking a third of something, eventually nothing is going to be left after you go all the way to the right. I guess I should make mention of the fact that that infinity is just a funky place, right? So again, you've been letting me get, you've been letting me get away with these 3 dots, okay? But again, there's some really weird things that happen when you talk about infinitely many things. So I just want to make it clear that our goal now is to add up all the numbers on this list. That's what I would like to do. I'm going to take 1 plus 1/3 plus 1/9 plus 1/27 plus 1/81 plus 1/243, add them all up. And again, we thought for a very long time that that was impossible. There's no way you could do that without getting infinity. So we thought that any infinite sum diverged. Every infinite sum diverged. Okay. This one is 3/2. It's 3/2, 1.5. Okay. So let's get an idea of why that is. Right. So let me go ahead and give a definition. Now, if I'm talking about doing something infinitely, of course, I need to invoke the fundamental concept in calculus, which is, of course, the limit. Okay. So what I'm going to do, in order to add up all of these, I'm going to add up finitely many, and then take the limit as that number goes to infinity. That's what we've been doing the whole damn time. Every time we want to say, the integral from 1 to infinity, we take the limit as t tends to infinity of the integral from 1 to t. And then let t go to infinity. Okay? We're going to do something very similar here. Okay, so definition, let a sub n be a sequence the partial sum, I'm going to use k here, okay? Let a sub k be a sequence. The partial sum s of n is simply what happens when you add up the first n terms of a sub k. S of n, partial sum S of n, S standing for sum. So again, we're using the sigma notation. Of course, all this means is A1 plus A2 plus A3 plus, right, all the way up to A sub n. That's all that means. Questions about that? A series converges if the limit as n tends to infinity of the sum k equals 1 to n of a sub k converges. As that gets closer and closer to a number. this notation, we have notation for this. This we're going to call the sum k equals 1. Suppose we'll start at 0. We'll start at 0. K equals 0 to infinity. Okay, it's okay. So again, if I have an infinity here, it means that I'm just taking a limit of a finite thing.
Does that have to be 0?
Oh, you can start any way you want, right? You can index things however you like. So starting at 0 is just notationally. You just decide to start things at 0. Okay. There's some formulas that are nice if you start at 0. It's just the way you want to write it. Questions about this? Let's do an example. So the example, let's do 1/3 to the n. Right. So now I want to look at a sequence A. It's going to associate k to 1/3 to the kth power. Okay, that's what A does. And now I intend to add up the first n terms. So S is going to let n go to the sum of A sub k. And then I want k to go from 1 to the first n. I just want to add up the first n terms. Okay. The first one. What's the first one? 1/3. Right. S sub 1 is 1/3. I'm sorry. I want to start at 0. Let me start at 0. I apologize. S sub 1, 4/3. Right. S sub 1, 4/3. Do we know why? 1 plus 1/3, right? It's the sum of the first two terms. The first term was 1. The second term was 1/3, right? So we just go back, right? So it's just 1 plus 1/3. That's S sub 1.
You say it will never reach 5.
It will never reach what? 5/3? I don't think it's ever going to reach 5/3. I think it's 3/2. I think it's 3/2. S sub 2. 13/9. S sub 3. 40/27. Right. So of course the question is, if I keep adding terms, will this thing settle down? That's the question. 100. What is that? What the hell is that, right? That's roughly something, right?
Mm-hmm.
And so obviously we're way more interested in the decimal version of this, right? I'll insert a command that allows us to do that, right? So eval f means to just get the decimal version of this. So evaluate it as a floating number, right? That's what eval f stands for. Evaluate as a float, right? So that just means a decimal for my programming people. 1.333, right? 1.44444, right? Right. So that's close enough. Right, so at least it's 1.5 to enough decimal places, right? So that's my hand-waving argument. I'm going to prove this in just a moment, okay? But it says that it seems like if you add up those terms, right, then you get 1.5. Now, I'm claiming that that's the limit. I'm claiming that that's what it converges to, but I need more evidence than that, at least psychologically. I need to show that all the other ones are like that, right? That none of them venture away from that number, right? So that means that when you keep on, now this is a crucial remark here, that from the 101st term that I've added, when I add the 102nd term plus the 103rd term plus the 104th term, I add up all of those damn terms, 900 of them. They don't even contribute to any of these decimal places. That's how small they are. I've added up all these terms to get from the 101st one to the 1001st one, and no term has been added to change any of these numbers.
Isn't that rounded?
It's rounded. It's rounded up to here. Yeah, right. That's right. So yes, there are tons of zeros, and I can extend the float if you want to, right? So we can see what those zeros are, right? So obviously there's some numbers back here. There's still some numbers back. There must be, right? Because I keep adding stuff. So obviously, there's still some numbers over here.
So if that, it should be 1.49999.
Which one? With which one? Oh no! It's yeah, obviously, right. It's 1.4999, absolutely, right. And so it is 1.499, right.
So it actually isn't then.
Forever, right? Forever.
Yeah.
No, that's right. It can't. So it'll never be 1.5, as he was remarking. And again, for 9,000 terms, you're not adding on. You're not adding anything, right? That is the requirement for a series to converge, is that you cannot be adding a lot of stuff as you go towards the end, right? And that's the theme, that it doesn't matter to a series in the beginning, it matters what happens at the end, okay? Questions about the idea of a series. The important functions I was talking about, Bessel functions and gamma functions, are all series. They're all power series. And so
the definition is that
a series converges if the partial sums seem to all be getting closer and closer to one number. So the series converges if the partial sums converge. That is the definition. Oh no, I wasn't defining series. I was defining what it means for a series to converge. So a series converges if the partial sums converge.
I thought you were defining what a series is.
Oh no, a series is just no. I define what a partial sum is, and then I will say that a series converges if this, and so we call this the series. Sum k equals 0 to infinity of a sub k. I just made a claim, and the claim is this, that the sum k equals 0 to infinity of 1 over 3 to the k power is equal to 3 over 2. That's what I just claimed.
And that basically means you start off at 0 and you're going to infinity.
You add up all the terms on that list. On the list that I had here, add up all the terms, all of them, 1.5, even. Questions about that? Now, I may mention someone in the class asked a relevant question. Said, again, why the hell is this relevant? Right? Someone asked, and I think I gave the example here, right? That, again, the typical example is you spend $1, there was an article that came out about how much the university or the college here contributed to Gwinnett County. Okay? And they talk about what $1 spent here meant elsewhere, right? Yeah. So that's not so surprising. So, you get $1 and then you spend some of it, you save 10%. That's right, we did talk about this, right? So you save 10%, but then you spend, 90%, right? So that 90% or that 90 cents goes into the community, and then some people save it, and suppose that they save 90%, then, or they save 10%, then that's 0.81, and then 0.729. And of course, what we would like to see, of course, is what happens to all of these things. We're going to add up all of these things, right? And that's an infinite thing. Now, of course, someone brought up the point that, well, you don't care about the infinite list. You only care up to 2 decimal places, right? We only talk about cents, right? And that person's right, obviously. But in the context of mathematicians, if we can get the whole sum, get the whole damn thing, right? Any physicist would come in and say, well, for most series, you only need the first 100 terms. But how silly would it be if I came in and I say, okay, we're going to talk about series, but we only add up the first 100 terms? That's absurd, because we can each create a series in which the first 100 terms don't matter, and it's about the next infinitely many, right? So we can't just talk about the first 100. We can't just talk about the first 1,000, because there are always sequences and series where those first don't matter. I have to remark that when we were talking about these types of open problems, that they've been solved, they've been verified for the first billion integers. Of course, someone would say, isn't that enough proof? No, that's not true. There are examples of theories that were true up to the first billion, 2 billion natural numbers, and then for the next one it was false. For the next one it was false, right?
I don't believe
So,
that.
no, that's true. I'm telling you. That is true. Yeah, I will give you, so you've challenged me, I will give you a source. Just send me an email to to remind me while I'm at a computer, and I will find that out. Yes, that is absolutely true. So we are paranoid about saying that something is true for every natural number. Okay.
But teacher, why is there 3/2? How?
That's what I'm about to prove.
Oh.
Right, but 3/2 is, again, I hope this gives evidence. 3/2 is 1.5. 3/2 is 1.5. Right, so what we've done is, I've added, what'd you say? I've added the first two terms, 1.3, and then the numbers look like they converge to 1.5. And now, at the behest of some, let's prove it. I will, of course, ask you to prove this in general, right, for extra credit. All right.
Like, what are you putting for the variable? Can be kitty free? That's the problem, right? Or how they kitty free on the screen?
Here's the reasoning. Here we go.
Okay.
I need to look at the partial sum. So I'm going to look at S of n. S of n is equal to the sum, k equals 0 to n of 1/3 to the k. I'm going to write that out. Okay. That's 1. When k is 0, 1/3 to the 0 is 1. Plus. When k is 1, it's 1/3. Plus. When k is 2, 1/3 squared. Plus. When k is 3, 1/3 to the third. Plus. 1/3 to the k. This is a little too big. 1/3 k power. Okay. Math magic now. Usually I give you more warning, but I'll remark that 1/3 times S of n. What is that? Now if I take each one of these and multiply by 1/3, what happens? That's right, 1/3 plus 1/3 squared plus 1/3 to the third plus, I might get everything here, but then 1/3 to the k plus 1, right? My intention is to do what? Oh, if I multiply everything by 1/3, when I multiply 1/3 to the k times 1/3, that's 1/3 to the k plus 1. Right? I have another one. You add the powers. This is 1/3 to the first times 1/3 to the k plus 1. Oh, or you're just asking how many 1/3s do you have? How many 1/3s do you multiply? Okay. Is that okay?
Just because the power of 1/3 is a 1, so you add that 1 to the k. That's why you get k plus 1.
Yeah, that's right. That's
Okay.
exactly right. That's exactly right.
Okay.
Yeah. I'm going to subtract. S of n minus 1/3 S of n is what? Tons of things cancel. What's left? 1 That's right. Okay. They each have something in common over here. S of n, right? S of n times 1 minus 1/3. I'm not going to combine 1 minus 1/3 yet, only because when I give you the extra credit, it'll be easy to just go ahead and mimic what I'm doing here. S of n is then 1 minus 1/3 to the k plus 1. I'm sorry. This is S of k. I'm sorry. Or these should be n's. I'll make these n's. I apologize. I'm saying S of n and I'm ending at k. They have to be n's, right? That's an n. That's an n plus 1. I apologize. That's my fault. We got to be good with the terminology. Those are all n's. So n plus 1. N plus 1. N plus 1. all over 1 minus 1/3. And we'll make a remark. And now what do I want to do with n here? N's going to infinity for sure. So as n tends to infinity, what happens to 1/3 to the n plus 1? Keep taking 1/3 of something over and over and over again. What happens to that?
It's smaller.
That's right. So 1/3 to the n plus 1 tends to 0. This was the remark that he brought up, right? When he said, you know, you have a power of something less than 1, you let n go to infinity, you get 0. So the actual sum is 1 over 1 minus 1/3.
Okay.
1 over 2/3. 3 over 2.
We went through all.
What does that say? 1/3 to the n minus.
N plus 1. This term goes to 0.
N plus.
And that is the proof. You know what I'm about to ask about 1/3. You think it's special?
Looks like it.
What if I put in 1/4? Absolutely. 1 over 1 minus 1/4. What if I put in 5/7? One over 1 minus 5/7. That's absolutely right. So I guess we have a theorem. And the theorem says that, well, the sum, k equals 0, this is called the geometric series.
There we go.
Yeah, I was just going to say that looks a lot like one of the formulas we've been using.
That's right. But the sum, k equals 0 to infinity of r to the k is equal to 1 over 1 minus r. I think this is true for every r in the real line.
And is r is the ratio of the first two terms? That's what we learned in discrete.
That's right. It is.
So what happens to k after you do the 1 over 1 minus r?
Oh, but k is going to infinity. K is done.
Okay.
This is not going to depend on k in the end. At the end, either you get a number or you don't.
Oh,
So look, I've added them all up. So I just happen to write notation there, but there is no k here. It's r, it's 1 plus r squared plus r to the third. It's all of them, right? So the right-hand side should not have a k at all. Okay? This is not true for every r. There's no way that this could be true. So earlier today, I had fooled some people in my earlier class, right? They went ahead and did it. They went ahead. Woo! Woo! Added up 1 plus 2 plus 4 plus 8 plus 16 plus 32, got -1. Right? Just added them all up. Right? This can't be true for every r in the real line. This is only true if what?
Absolute value of r less than 1.
Has to be less than 1. Because that's the only way this proof works, right? This worked because 1/3 was less than 1. It's the crucial moment is here that you have to invoke. This would not be true if this was a 7, right? Because 7 to the n plus 1 does not go to 0. It's only those things that make this go to 0. And that means 1/2. That means 7/8. That means 5/7.
Only less than or equal?
Oh, if it were 1, right? Let's see what happens at 1. Let's do it. I want to take the sum of 1 to the k. K equals 0 to infinity. What is it?
0.
1 to the k is always 1. 1 plus 1 plus 1 plus 1 plus 1. What is it? That's infinite. It's not going to work. So it has to be strictly less than 1. It has to be strictly less than 1. Okay. So I'm being biased. I can add up powers of -3/4. I can add up powers of -3/4. 1 minus 3/4 plus 3/4 squared minus, I can do that too, right? Questions about this? Oh, by the way, this is extra credit. Prove that. Ha ha ha! My man. Even or odd?
Even.
Even. We'll make it. I think it's pretty good. I may erase that. But what do? We go here. R squared. R to the third. What is R? Everything is just wherever there's a 1/3, you put R. You'll need this R to the n plus 1 to go to 0, but that will mean that you need at some point to say that the absolute value of R is less than 1. If you don't say that, I'm marking it wrong. You get 0. Right? Because the proof doesn't work unless the absolute value of R is less than 1. Right? That's the crucial statement here. Okay. And then you get 1 over 1 minus R. That's the game. Okay? So, I mean, you just mimic the same proof, the same lines. It should make it less now. But I'll keep it at 4. Okay. Any questions about what I'm asking for the proof? So it's the same things we've done here, right? But instead of 1/3, we do it with R. Now let me just say, 7, 8 years ago, I would have done the proof with R first, right? And then I would have lost everybody, and then, it would have been no point. But usually now I do it with a number and then give it to you for points to prove the rest of it. I think it's better that way. Questions about what I'm asking?
This is the 2K one, right?
Say it again?
Is it the 2K one or the 1?
What about, wait, which one?
Which one are we proving for the extra credit?
Oh, no, we're proving that this is true for every R.
Okay.
When the absolute value of R is less than 1. I want you to prove this. These are absurdities, right? I guess I should put a big-ass X to this. This is outrageous. No way.
That looks like an important start.
I know.
Like the links that
Yeah, that's what I was just thinking now.
Like the, oh yeah, that's right, that's right. All right. So that's something to keep in mind, that you just can't invoke this for any real number. Both of these arguments here do imply something about what we want for series. And we've said it in the on Maple, that for a series to converge, the terms have to be getting smaller and smaller. There's no way around it. Okay? That is a requirement, right? So that we can get rid of bad examples like this. And this confused us for a while. We wouldn't have something like this. Okay. Now listen. There shouldn't be a problem with this. 0, you get 1, minus 1. 1, minus 1. 1, minus 1. I may get some extra credit for this one too. I want to add up everything on the list. What do you get? 0. Right. You get 0. 1, minus 1, plus 1, minus 1, plus 1. You get anything else? Can you get 1?
Depending on where you stop.
I'm not stopping. I'm adding them all up. Can I get 1? Can someone give me 1 here? No? Doesn't depend on where you stop. It may depend on where you start. Right? I'm not gonna. Let me just hold that one. I'm gonna hold that one. So minus 1 plus 1. What's that?
0.
Minus 1 plus 1. 0. So my total's still 1 so far. Minus 1 plus 1. All of that's nothing. The answer's 1. Can someone get me 2? Can someone give me 3.5? Right. So I can make it 2. I can make it 5. Right? Because there are infinitely many of them. Right? One of the great mathematicians, David Hilbert, at the turn of the century, the 1900th century. Right? At 1900, he was at a conference, and he gave the very problems that are worth $1 million today. Right? He called those the Millennium Problems. Right? So he gave those problems a long, long time ago. But he's famous for an example like this. So if you have, suppose you have a hotel. It's called Hilbert's Hotel. If a hotel has infinitely many rooms, and you put infinitely many people, in that hotel. So there's a person in each room. And then someone comes to the hotel, and they want a room. How do you give them a room? Say it again? That's right. You shift everyone to the next room and put them in that first one. Right? That's the problem with infinitely many things. Okay? That's what we've done here, right? So if we want to preserve our notion of adding things up, right, then we have to be really, really careful. We have to be really, really careful. We can't just add things up in any order or anything like this. if we're going to be this lax, right? So this fails. In order to add up infinitely many terms, all the terms have to be getting smaller and smaller. It's called the nth term test. Let's write it. If the sum k equals 0 to infinity of a sub k converges, that is to say, if I add up all the numbers on the list, that is a sub k, then it better be the case that all of the a sub k's better be contributing nothing. I mean, they've just got to be absolutely nothing. So this is called the kth term test. Actually, they call it the nth term test, so I got to use n. Then this tends to 0 as n tends to infinity. And all I'm saying is that if you have a list, an infinite list, and you keep adding stuff on, then you better not be adding on a lot. Actually, you better be adding on practically nothing. Right? There's no way you can add on a constant amount. Right? You can't. The amount can't stay the same. Right? There's no way you can have a sequence and then all of a sudden all the numbers stay at 1 over 1 trillion, because even if you add 1 over 1 trillion up infinitely many times, it's going to be infinity. Right? The numbers certainly can't get bigger. You can have a list of numbers, and after some point they start going up, and then expect to get a finite number. You get infinity, right? The only option is for those numbers to just completely vanish. Okay? This is not that difficult to prove, right? Right? So if you prove this by contradiction, right? The great skeptic comes in and says, well, you know what? I don't believe this is true. Right? I don't believe this is true. And he says, well, if you think that there's a series that converges, you add up all the terms on this list and somehow the numbers don't get smaller. And he says, of course, that's right. And he says, well, if you don't think the numbers get smaller, then they stay away from 0. And he says, yes, they do stay away from 0. And I says, well, are they all bigger than 1 over 100? He says, yes. After some point, the terms of the sequence are all bigger than 1 over 100. And you say, oh, that's interesting, because let me know when. And he says, oh, after the 10 millionth term, they're all bigger than 1 over 100. And then you simply remind him that if you add up 1 over 100 from 10 million to infinity, that's infinity. And he says, well, no, that diverges. And he says, oh, you're right again. Right? So if you don't think it goes to 0, it has to stay away, and you just have to tell me what you think it stays, how far it stays away, and then I'll give you infinity in a moment. Right? So that's how the proof goes. Right? So if you add up all the terms, then it has to go to 0. And here is a context where I have the luxury of giving tons of true-false questions. Right? True or false? If a series converges, then the sequence associated with it must converge to 0. True or false? If a series converges, then its associated sequence has to converge to 0. That is true. That is true. Right? That's true. Okay. If I have a sequence that goes to 0 and I add up all the terms, then I'm going to get a finite number. Is that true or false?
I'm sorry, could you repeat the question?
Absolutely. Because I'm asking this exactly on the test. If I have oh, now you pay attention. Look, I see some people start writing, taking notes, all this. Wow. I just need to mix that up. And then for everything now I'm going to say for the rest of the time is going to be on the test, right? Every fucking thing I say. Okay? Now, I didn't know I had to just say that to get people to pay attention. It's unbelievable. I wish you had the views that I had. People were just like this. Okay, test. Okay. So what I'm gonna give you a counterexample in a moment. What I'm about to say is false. Okay. So this only works in one way. If P implies Q here, not Q does not imply P. Okay. So if I give you a list and I can add up all the numbers and get a finite number, that's what that first thing said in words. I'm adding up all the numbers on this list and I get a finite number. Then the numbers on that list have to vanish. In English, that is exactly what that's saying. And you could say that to someone on the street. All right? So I may ask that. Explain what it means for a series to converge. All right? And that's what it means. That you can add up all the numbers on the list, on an infinite list. That's all it means. Okay? I'm going to go the other way and say, I'm going to give you a list now. And all the terms vanish. And now I'm going to add them all up. Can I get infinity or not? 1 over x. That's right. At least when we integrated 1 over x, right? When we integrated 1 over x from 1 to infinity, we got infinity. And now I'm asking about adding up 1 over n. And if somehow the area under 1 over x is infinity, I don't think I should be able to add up 1 over n. Right? So that is the classic counterexample. Right? That the sum of 1 over n equals 1 to infinity is infinite. Right?
I remember that as you said that dividing by infinity is the same thing as going to infinity.
Okay. And so what is this? What am I saying about this? 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus... I'm making that sound on purpose. I'm not dying. Okay. Versus 1 plus 1 over 2 plus 1 over 4 plus 1 over 8, right? Plus 1 over 16. This thing's flying to where? Plus 1 over 32, right? Look at the difference between these two. You know? One's doing what? One list is going where really quick? 0. This list is going to 0 really quick. This list goes to 0 as slow, just so slow, right? At the same pace as the index. N is becoming 1, 2, 3, 4, and this is just mimicking it, right? It doesn't go to 0 fast enough, right? For a sequence to converge, the sequence has to go to 0 fast enough, and this is the cutoff point, 1 over n. In a similar way, of course, this never had a chance. That goes to 0 even slower, right? We'll come up with a rule for this one. Okay. Now, of course, this is a claim. We'll put it here.
The second one, if a sequence goes to 0, then the series is converged.
Right.
That's false.
That's false. I'm about to demonstrate that with this counterexample. A sub k, I want it to be 1 over k. And this is not going to be sufficient, right? This is going to tell you the inability for Maple. I'm not starting at 0, because if I would start at 0, I would be dividing by 0, so I'm starting at 1. Okay. S at 1 is 1. 1 over 1 is 1. Add up the first two, should be 1 plus 1/2, that's 1.5. First 3, 1 plus 1/2 plus 1/3, okay, that's that. 100, 5, 101, uh-oh, 5.19, 1,001. Let's just make sure, let's see what happens, because the great skeptic is here now and says, wait 1 second. You're trying to tell me that this is going to infinity, yet in 900 terms you've only gained 2 points. Right? 2 point something, right? You've only gained 2 points in 900 terms. How many do you gain in 9,000? Only 2 more. This is going to infinity? Right? It's almost like the natural law, right? It's not going to 0, that's right. Oh, no. Wait 1 second. But 1 over n goes to 0. But here, look at what happened. So I keep adding terms. Now remember, for the one that did work, that after this point, we weren't adding anything. We were adding nothing, right? But after the 10,000th term, and for most of the sequences that I'm going to give you, after the 10,000th term, the discussion settled. You're not adding anything else. But now, after the 10,000th term, I'm still adding 2 or 3. I'm going to push Maple. You want to push it? You want to break this thing? It's pretty remarkable I can do that like that, right? It might have a formula, right? I think it's using the natural log, because it's the antiderivative of 1 over x. So it's about 19 here. Okay, so what is that? 3, 6, 100 million. 100 million and 1, it's almost 20. Okay. Again, we're using the fact that we have an infinite list. We haven't even gotten started. Haven't even gotten started, okay? What I do want to mention is I simply cannot use this to convince you. Right? This is, again, the triumph of mathematics. That, as much as I can hand wave and use this to show that something goes to 0 or converges, in order to show that this is infinite, I have to do something else. Here's the proof. Here's how the proof goes. So the claim is the sum, I'll use k. K equals 1 to infinity of 1 over n is infinite. Wow, I haven't done this proof in a long time. Maybe 5 years or something like this. Wait, whenever I had the last test, 2006. Limit, oh no, I want to look at S of n. I'm sorry, if I'm talking about this in terms of k, I should put a k here. I get my k's and n's mixed up. All right, so I just want to look at the first n of them. This is equal to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/9. That's 1 over 10. Bear with me, I'm writing these out. Let's make a point. 13 plus 1 over 14 plus 1 over 15 plus 1 over 16. And again, I have not even gotten started. Okay? Here's the point I want to make. I want to remark something about this, right? So here, this is 1. I'll leave it. That's 1/2. I do want to make a remark about these 4 things here, right? So all of these are bigger than an 1/8. They're all bigger than 1/8, right? If they're all bigger than 1/8, then you add them up together, that makes them all bigger than 4/8. So together, that's all bigger than 4/8, which is 1/2. Is that okay? Each one of these, 1, 2, 3, 4, 5, 6, 7, 8, each one of these, I'll put them in blue, all bigger than 1 over what? 1 over 16. And there are 8 of them. So this whole thing in blue is bigger than 8 over 16, which is 1/2. And that does not stop.
It's always less than 1.
Right? No, but I keep adding all these terms, and I can keep grouping them forever. I can always get a group that's always bigger than 1/2. Right? And so you can show by induction that this is bigger than 1 plus 1/2 plus some constant, and again, and here it's going to be the sum, k equals 1 to infinity of 1/2. And so the induction proof, I think, is in the book. Okay. But again, I'm not. It would take me. Hopefully, they spent a whole class on induction in discrete. I hope. Have you all talked about induction yet? You prove P of 1. Then you show P of k implies P of k plus 1.
Would you teach
No?
it if college algebra was a prerequisite for the course?
Yes. Oh, yeah. Yeah.
Maybe we'll get there.
Okay, good. Yeah. Oh, yeah. I think it should be in the
I mean, that's
course,
the
yeah.
biggest problem, though, with the class in the book and stuff, because there's
There are
very
a lot of
little
different people. Okay.
prerequisites.
Are you all taking the same discrete class? Okay. Okay. All right, so that's infinite. Okay. So you just keep adding on more and more. Now, of course, from what we've just seen, I needed 4 terms to get the first 1/2. I needed 8 terms to get the second 1/2. So I'm going to need tons and tons of terms to add up to get that extra 1/2. But they're there. They're there. There are infinitely many of these things. So you're going to have it. So, but that explains why it goes to infinity so slowly. Because it takes so much time to get that extra 1/2, right? So you add up 1/2 more and more and more. Okay? So, you can have a list going to 0 and add up the list and get infinity. That is true. Okay? This does hint to us a statement about the sum k equals 1 to infinity of 1 over k to the p. And I'm going to use n here. This converges if and only if one over n to the p goes to 0 fast enough. And that only happens if p is bigger than 1. This is called p-series. Okay. So now, let's throw something together. We need to talk about some test questions here. All right, so going back, test question number 3, right, 3 or 4, says, well, what in the world is the sum k equals 0 to infinity of 2 times 6 over 11 to the k power? That's A. Say it again? Yeah, it's new. We just haven't used the geometric series yet in test context. The sum k equals 0 to infinity of 1 over 2 to the k. That's what I had talked about earlier. Remember, I did this on a number of occasions. Remember, I created the box. It was of area 1. I created a copy of that box right next to it, and then I just kept cutting it in half and half and half and half. That takes care of that. That's going to be 2. Okay? And then the sum k equals 1 to infinity of 3 times, let's say, negative 1. Let's not do that yet. Let's do 2 over 7 to the k. As you can imagine, there are tons of lists. Okay. So the first one we talked about was called geometric. So it's just the power of one number. Right? We have already mentioned that in order for that to work, that number had to be less than 1. Right? So you can have 1/7 to the first 1, and then 1/7, and then 1/7 squared, and then 1/7 to the third, and so forth. Okay. That's a geometric series, right? So I'm going to give you a list, or I'm going to give you a series, and I'm going to say, determine whether the following converge or diverge. Right? You'll look at this one, you'll look at A, and you're going to say that converges because it's geometric, and 6 over 11 is less than 1. Okay? Yes. Right? So for these, though, I'm going to ask you to actually find the number. Okay? Because you can actually find the number. The other ones, like, we'll do one in a second. But these, you can actually find the answer. Other ones, you just can't find the answer. So I'm just going to ask you whether it's a number or not. whether it converges or not. Okay. But for these, what's the number? 2 times 1 over 1 minus 6 over 11. Now, I've done something weird here.
I thought that was a constant.
It is a constant, and so therefore we can bring it out. Now, listen. He wants to play some games now. Now, if I have 2 times x plus 2 times y, right? They both have 2. I can pull out the 2 and then have x plus y. I can do that with 2 elements. I can do that with 50. I can do that with 500 million. You want me to do that with infinitely many, right? It's not so obvious that we can do that, but we can. We can do that, right? But we haven't made that clear. You can do that, right? So if you have a list, right? You have a list and it converges to 15. I take your list, add up all the numbers, and you get 15. Now I'm going to get a new list. And my list is going to take everything on your list and multiply by 3. And now I'm going to add all of those up. What should you get? 45. And you do. Okay? That's not difficult to prove. Right? You all come up with a list. It's brilliant. Adds up to 10. You all come up with another list. It's equally brilliant. Adds up to 35. I don't know why I like 45. Adds up to 20. Okay? Now I'm going to create a new list. Doubly brilliant. It's going to take your list and add it to your list. Right? My list should add up to 30. No problems there, right? Just got to get those things out of the way, right? Whenever you introduce new things, you got to do the typical adding, subtracting, and all of that stuff, okay? I'm not going to write those things down. They appeal so much to our intuition, right? So if you converge and you converge, you can add up and get something that converges, okay? What if you converge and you diverge to infinity? You add them, infinity. What if you converge and you diverge? You add them, converge or diverge? There's something. No, I didn't. Now, earlier we talked about diverging to infinity and just diverging. Right? Can you think of a sequence that just diverges but not to infinity? Right, so we said minus 1 to the n. I think you mentioned that, right? So minus 1 to the n bounces. Right? There is no one number that goes to. Right? So that diverges. Okay. So you converge, you have a series that converges, you have a series that diverges. Can the converging one fix the diverging one if you add them together? So let's do it, right? So a sub n, and let's just talk about say it again. Well, negative 1 to the n does not converge. Now I want you to add it to something that does converge and see if it converges. Okay. So a sub n converges. A sub n goes to a. B sub n diverges. And now I want to ask about a sub n plus b sub n. Oh, it is not. This is something different. So we'll cut it off. Thank you. The question now, converge? Converge? We'll prove this by contradiction. Okay. What if it did converge? That's exactly correct. Right? You're really good at the proofs by contradiction. Right? Why would it have to converge?
The other one would have to converge.
Right. So if a sub n plus b sub n went to c, and I know that a sub n goes to a, then b sub n has to go to, what is it? C minus a. That's absolutely right. There's no way that this is going to a number, the whole thing in totality is going to a number, and all of a sudden b sub n is being an asshole. There's no way. Right? So if you assume they converge, then we contradict the fact that this diverges. That means that it has to diverge. Right? That's a proof by contradiction. I guess I should talk about that very clearly. If you want to prove something by contradiction, right, P implies Q, right, then one way to prove it is to just assume that Q doesn't happen and so that something absurd must occur. Okay. If you assume P, if you assume Q, and follow the necessary steps. And all those steps are things that we know to be true, and you arrive at something that is just ridiculous, then the thing you assumed must be wrong. Right? And therefore, you can't assume not Q, the answer must be Q. Right? So we said that it seems like A plus B, A sub n plus B sub n, that either converges or diverges. Well, if it actually converges, then we get that B sub n has to converge too, but we just said it diverged, so that's a contradiction. What did we assume? We assumed it diverged. That can't be right. I'm sorry, we assumed it converged. That can't be right. Okay. Let's write the rest of these. We did this 1 over 1 minus 1/2. That's the game. That's 2.
And do the same thing for 3 will be 3 times 1 over 1 minus 2.
3 times 1 over 1 minus 2/7. And what do I have to do?
What?
There's something else I have to do here.
What about the k equals 1?
Right. I didn't start at 1. I didn't start at 0. I started at 1. So now I've left off the 0th term. What is that term? It's not 1. It's 3. It's 3 times 1. So now I have to subtract off the first term. So if you start at 0, that's all the terms. Right? If you start at 1, you left off the 0th term. And so now you get everything, that you get all the terms, and you need to take off the first one.
So the 3 times 1 over 1 minus 2/7 is...
That's if you added from 0 to infinity.
Okay.
But I'm asking for 1, and therefore you add up to from 0 to infinity and then subtract off the 0th one.
Okay, so even though it says k is 1, you still have to start from 0, is that right?
Well, this thing here is the sum. I need to put it in a different color. We've showed that this thing here is the sum, k equals 0 to infinity of 3 times 2 over 7 to the k power. Right.
And then the minus the 3 is the actual 1.
Minus 3 is what happens at the first term.
Okay.
Right. So if you take off the first term, then you get from 1 to
So
infinity.
if k was to 2, you would still have to include all of those and then the second one?
Yeah, that's right. So now if I wanted to sum k equals 2 to infinity, I need to add up all of them and then subtract off the first term, which is 3, and the second term, which is 3 times 2 over 7 to the first. Okay. Questions about that? Questions about what I would ask? Now, these are pretty straightforward. And there's some tricks you can play here. Let's play some of these tricks. They're not that impressive. So now, what if I just start playing with this formula, the sum? So I've already played with the index. So maybe I'll play with the index. I won't start at 0. You know what to do now if I don't start at 0, right? If I don't start at 0, then you need to add in. Maybe we should do some more examples, right? So, but I'll play with this one. So these are just tricks. Right, now remember, we know sum k equals 0 to infinity of r to the n is 1 over 1 minus r, as long as the absolute value of r is less than 1. Now if I give you something that looks slightly different, you just need to transform it. Here are the following tricks. The sum k equals 0 to infinity, all of a sudden now, what if I have 3/4, I'm saying minus 3/4 to the n plus 2. So all of a sudden the power is not n all of a sudden. Right? We're just gonna take control of the problem, make it n, and pay for it later. Okay. What if I now say, well, what is the sum? I'll do another one of these. The sum k equals 2 to infinity of, I'll do this in a couple of ways. Let's say 7 over 8 to the, I'll make it 7 over 8 to the n power. And what if I say the sum, I think those are all the tricks I can do here. K equals, yeah, I think that's it basically. I can play with the index and then I can play with the thing you're adding. But anything that remotely I'm going to use for this is going to come into it. Either I'm playing with this power or I'm playing with the index. Right? They always turn out to be equivalent. How do I turn this into what I want? I simply make the remark that this is equal to the sum k equals 0 to infinity And then I'll say, well, listen, this is minus 3/4 to the n. I need that. I'm going to put it there, and everything else I'm just going to pay for. But it's times what? Minus 3/4 to what power? Yeah, n plus 2. And you just, absolutely, you just pull it out. So I'll move this later to finish this problem.
You need an extra sheet of paper.
And this is equal to, yeah, right? This is equal to, I just pull that out, that has no dependence on n, I apologize, n. This is equal to 9/16 times the sum, n equals 0 to infinity of minus 3/4 to the nth power. And that game's over. 9/16 times 1 over 1 minus negative 3/4.
And then whatever you get is the number that converges to, right?
Yeah, absolutely. That's exactly right. But you know me. I'll take questions about that. What is that?
9/20.
4 over 7? 36 over 112, something like that?
9/28.
9/28.
No.
Yeah, 9/20, yeah. 9/28. Questions about that? All right. So if somehow the power is, a little bit different, we shouldn't be intimidated by that. And then I had the index changed a little bit. I can leave it here. We'll put it in a different color. The sum k equals 0 to infinity. Let me use n immediately. N equals 0 to infinity. I'm sorry, and I meant 2. Somehow, if I change the index to 2, to infinity of 7 over 8 to the n. Right? We'll remark just pretty quickly that, well, this is what would happen if I just add up all of them. So I'm just going to add up all of them. And I'm going to do that because I know what that answer is. Right? And then I need to subtract off the first one and the second one. And in some cases, I should say, the 0th one and the first one. So if I'm starting at 2, that's the same thing as adding them all up and then subtracting the first 2. Yes?
The other example was trickery. What if n is minus?
Oh, if n is minus, then you just pull out minus 3/4 to the minus 2.
Okay.
Right, and that's 16 over 9. You just flip it. Is that okay? But we know this. This is just 1 over, because 7 over 8 is less than 1. 1 over 1 minus 7 over 8. Minus 1 minus 7 over 8. Okay.
So the first one is the 2, and then the second one is the 1, and the last one is the 0?
Wait, here?
Yeah. The 1 over 1 minus 7/8, is that the 2?
Oh, no, that's this. So all I'm doing is replacing. So the theorem you're going to prove for extra credit says that this is equal to this,
Okay.
and these two things remain the same.
Should be 29 over 8.
For this whole total?
Yep.
49 over 8. Okay. I'll take other questions about this. Classic one we have to do, one of the applications of sequences of series, 0.9 bar. What is that? That's 1. That is right. That's 1 for sure. 0.9 repeating. Intuitively, why is that? Intuitively, you can see that it's 1 simply by taking the difference. What's the difference when you subtract? 0.0 bar. Sounds like 0 to me, right? 0.0000000, right? Where do you ever put the number there? And when I was trying to prove this in real analysis in undergrad at Howard University in Washington, D.C., I did not know the argument that I'm about to give. And so the homework there, I was like, well, 0.99999, right? You subtract 1 from it, and there's no place to put the 1, and so it has to be 0. Somehow I didn't get any credit for that, right? Not as a math major, at least. Okay, so this is how you do it, right? So 0.9 bar, this is a claim, of course. By the way, you can prove this for 1/3. 1/3 is 0.3 bar, right? And so, and by the way, you only need to prove one of those two in order to prove this, right? So either you prove this and divide everything by 3, and you get the 0.3 bar as 1/3, or you prove that 0.3 bar is 1/3 and then multiply both sides by 3, and you get this, right? So they're equivalent statements. So 0.9 bar is equal to 0.9999 dot, right? And those 3 dots again, right? That equals 0.9 plus 0.09 plus 0.009. And then hopefully we see that when we write 0.9 bar, we're talking about an infinite series. We've been doing infinite series since the second in grade. Right? The moment they had the bar there, we were talking about infinite series. We'll remark that they both have 9 in common. More than that, they both have 0.9 in common. We factor it out. That leaves us with 1 plus 0.1 plus 0.01 plus 0.001 plus dot dot dot. This is equal to 0.9 times, and then we'll remark again that 0.1 is just 1/10, and you can see why it's better to write this as a fraction, because then we start to just scoff and say, oh, this is nap time. We're just adding up powers of 10. Powers of 1/10. And you say, oh, well, this is just the sum, k equals 0 to infinity of 1/10 to the k. You know what that is? I showed in extra credit that that's just this. 0.9 times 1/0.9 is 1. Questions about that? So it's a classic example of using infinite series to get decimal expansions.
I have a question. So
Please.
if you square 0.9 and if you square 1, then that would be a difference, right? So would that prove that wrong?
Oh no, but you're absolutely right. If you square 0.9, right, you're supposed to get something. You're supposed to get 0.9, right? If you square 0.9 bar, you're supposed to get 0.9 bar. Right?
That's what I was thinking.
Yeah, that's what you're supposed to get. Right? And don't worry, when we start doing some serious ones, you're going to get all these crazy infinite series formula. Okay. And one of the nice ones is that E, we'll prove this, E is the sum, k equals 0 to infinity, of 1/k factorial. That's E. But it's actually pretty freaky, because 1 plus 1/1 factorial plus 1/2 factorial plus 1/3 factorial plus 1/4 factorial, right? You add these up forever. Right? These are all rational. Right? These are just all fractions, and somehow you add them all up, and you get the farthest thing from a fraction. Right? The exponential is transcendental. I mean, it's irrational, right? So it's certainly not a fraction, but even worse than that, it doesn't even solve. It's not the solution of any quadratic with integer coefficients, right? So it's a very weird number, but it's coming out of very nice fractions. Right? But adding them up infinitely gives you some serious problems, right, in terms of being rational. Right? So that's one of them, but we'll prove that later. Okay. And so then the next question will simply be about p-series, right? So then question number 4, as I had it listed, and we may reorder these, is determine whether the following converge or not, converge or diverge. Determine if the following converge or diverge. Now this is the beginning of, this may be the last question on the test.
What?
And and here's the reason. The reason is because,
More questions?
well, the rest of it, yes, that's right. We're going to spend the rest of the chapter figuring out which lists converge and which other lists diverge. Okay? Right? So, you know, I'm just going to give you a shit ton of them. There's going to be a ton of lists. And you have to say, okay, that one converges because of P-series. For instance, I know that the sum, n equals, and again, who cares where you start, n equals 7 to infinity, 1 over n to the third, converge or diverge? Converge because 3 is bigger than 1. That's exactly right. And that's what you have to write. You have to write that, right? So you have to say it converges by P-series because 3 is bigger than 1. Okay. Questions about that? Say it again? Oh yeah, I'm gonna give homework about this. Absolutely. Okay. So we'll end there. Next time, we're just going to keep adding to the list. Okay.
I have a question.
Yeah, please. I'll end class there.
For this semester,
Yes.
we're covering chapter 8,
8 and 9.
8 and 9.
Yeah.
Is the test push back a week?
Yeah, we can do that. That's not a problem. Yeah, that's fine. Where does that take us? To the, oh, no. But see, that's right. That's the week of Thanksgiving. That's why I didn't want to have it then. Unless everyone's going to be here.
I don't think we have classes.
We don't.
I don't think so, right? Okay, yeah. So that's why I wanted to have the week before. We'll have the week after, the 29th then. Yeah.
Wait.
Okay, we're good. Say it again? I was about to say, where is it? What happened? Oh, okay. Okay, so you just didn't want to admit that your PC did something unmatched-like. Okay.
The unmatched-like character is 5 years old and weighs 6 pounds.
Okay.
So if that was n to the 1, then it would
Diverge.
diverge.
Because 1 is not bigger than 1.
Okay.
Yeah.
So if it's greater than or less than 1, then it will diverge. I mean, equal to 1 or less than 1.
Yes, it diverges. That's right. That's right.
I know you won't be using this, but I saw a solution to a logic problem that did this, but how do you interpret a double factorial?
Right. So I don't see what the problem would be. So
What do you think about that?
also, I mean, you have to do the first one and then do it again. That number is obscene.
Oh, so
right?
you just take...
So you take 10. Now, I think that's true.
Yeah,
So
that's
I think that actually has because I think that actually has a definition. So I don't. It's not clear to me that n factorial
So if you do
is.
3 factorial, you would do the factorial of 3 and then the factorial of
No.
I don't think they're the same.
It's not like prime where you do
It might be. So the question is that 6 factorial, right? Which is 720. I think this has a different terminology, but I'm not sure.
I need you to prove that 6 factorial is 720.
6 times 5 times 4 times 3 times 2 times 1?
Do you have a copy of the test?
Yes, they should be right here. Here. There you go. I'll be putting them up. I just wanted to make sure everyone hadn't taken it. So I'm putting them on Blackboard.
I don't know ink in my printer, so I figured I'd ask if you have.
Oh, no worries. It's going up on Blackboard soon, so.
Well, I think it's still
Are we still recording? Thank you.
See you next week.
Okay.
The weekend.